You're being laid back here. This is a laid back summer school, so we're but the error will not decrease by itself. Somebody has to help me out to decrease the error. And you guys are going to be exactly these people that are going to help the neural network succeed in its whatever it's doing. That's the spirit. You have already eaten, right?
I've already eaten it.
Then that's the spirit. Anyway, welcome back. So just to recap, refresh, after coffee, cookies, we have just ran through the entire feed-forward pass. We have generated the class scores of every neuron, and now we know how much we are off the target. Right? So we have calculated the error, which is basically a measure of how much we missed the target. And the target was 0, 1. Was it 0, 1, or was it 1, 0? No, 0, 1. And we have calculated the error, and it's 0.305, and it's huge. And we want to make it smaller. Now, the question that I have for you is, what are the ways to make it smaller? What can we do to make it smaller?
Try to change parameters.
We can change the parameters, right? So this is actually the only way, reasonable way to make it smaller. What else can you do? Maybe somebody comes up with a breakthrough. We'll write a paper together.
Change attribution.
Change input.
Change input, you can also change the input. That's totally doable, right? You can change the input. You're laughing right now, but there are methods that do exactly that. They backpropagate not to the weights, which we're going to do now, but they're backpropagating to the inputs. Do you know why they do that? Why would anybody do that? Think about this, but we'll...
Maybe they can see how should input change, like how the input changes are.
So why they do it is that they would like to analyze which parts of the input causes the error. And that is very useful if you think about this. If I'm looking at images, and I'm working with images, then which of the parts of the image are causing that specific behavior, right? So that is pretty interesting. But normally, we obviously don't change inputs if you want to change the error. So we only change these things, right? And obviously, with changing weights, we would like to make the predictions match the truth. Right? So that's the way to decrease the error, is to make the predictions match the expectations. So the way is to do the weights. Here already somebody said, look, we can actually change the inputs. We can, but this will compromise this, so we're not changing the inputs. Never change the inputs at home. Please don't do it. Unless you know what to do. I mean, unless you have authority for doing this, don't do it. So we're going to change the weights and biases in an attempt to decrease the error. Now, I know that you all know enough to play with me and tell me backpropagation is the way, or maybe some of you know that the backpropagation is the way. But if you wouldn't know the backpropagation, what would be the naive thing to think about when you think about, let's say, W5, here, this one, the one weight. We are focusing only on one weight, not all the others. How can I change W5 to decrease the total error? Sorry?
We have like this equation, and we want this equation to be equal to 0 because that's equal.
Yeah, okay, this one should be 0.
So we are.
But if you don't, if there are hundreds of ways in between so you don't know what's the actual relationship. So what can you do to see how do I change W5 to decrease the total error? Sorry?
Plot it, like how the output changes based on weight 5.
Or simply saying you can, what you can do is you can just say, well, basically what you can do is you can say, I'll try different W ones, right? And I'll see how that influences my total error. So for example, I can say I want to increase it suddenly, and my total error just got bigger. I'm like, uh-oh, that's not the right way to go. I want to go the other way. Okay, then let's go back. And we go downward. And we see that by going downwards, the total error decreases, right? However, there is a problem with this approach. What is the problem with this approach?
You can guess.
Yes, but let's take the overfitting out of the picture right now.
Which
Only with the model.
you can get stuck in a range of numbers.
You can get stuck because the cost functions in normal neural networks are very non-linear. They're highly kind of weird shapes and weird shaped surfaces. What else is the problem? So imagine, the approach that I'm trying to test here is that I'm saying, look, I am going to randomly tweak every weight and see how that influences my total error. What's the long? It will take me ages, eons to do that. Maybe on this one, it's maybe fine. But in general, if I'm going to do it on every other weight, it's just going to take me too much time. And also, sometimes, it may not be that linear that I change this one and the error drops, and then maybe this changes the dynamics of the relationship in the other place. It means that I have to redo all my work, which is totally unreasonable thing to do. Does anyone see where I'm getting? I'm getting at the time a place where I'd like to say that we don't want to do that for every weight. We would like to calculate something called gradient. And the gradient is basically a direction of a function that tells us what? What does the gradient show? Where the gradient, so let me tell you this. Gradient is a direction. Where will we arrive if we go along the gradient? Maximum value of the function. So if we go along the gradient, we will arrive at the largest ever possible error you can imagine. How nice is that? Not at all, not at all. So we look at, we say, hey gradient, where should we go? And the gradient says, there. And then we say, thank you gradient, see ya. That's why we calculate the gradient. So we want to calculate the gradient. The gradient shows the greatest increase of the function. We don't care about the increase of the function, we care about the exactly opposite, right? We care about the decrease of the function. So that's why we go downwards. We try to find the minimum of the function, the minimum of the error. This is what we are about. This is way too optimistic. This error function, so this what I'm plotting here is how does my error change with respect to this specific weight? And that's very optimistic, normally influence. But people have shown, even theoretically, that even, and the other problem, of course, is this is just one weight, right? And there are normally, how many weights there are normally in neural networks? These days, current, present day neural networks. Billions of weights. So this is a billion-dimensional picture that looks like this. And what people have shown is that even in this billion-dimensional surfaces, hyperplanes, you can find minimums that will be reasonably good, that will be close to the global minimum using gradient descent. So this is what exactly we're going to do, is the gradient descent. And we're going to demonstrate the gradient descent on a very small scale, just with respect to W5. So basically the question that I'm asking from you, from myself, from the slides is that how am I going to change W5 to decrease the total error? What is the kind of value by how much I should decrease it, but also how do I do it? And in order to respond to this question, I need to calculate the gradient of the total function with respect to W5. Basically, this is direction in which the function yeah, basically, I have the next slide. Direction in which the total error is going to increase, but we'll just take, we'll multiply by -1 and we'll go the opposite direction. Okay? Does this make sense? Questions? I know when people do this is a bad sign.
Why only to be 5? Is it like an example? Or
Oh yeah, this is just an example. So currently we are looking at the gradient descent at the very small zoom level, just to see.
so like we're doing it for every grade?
No, we are not going to do it for everything. We'll just do it for W5, and then I'll say matrices. Any other questions? Any other questions? I see questions. Ask it. Okay, crystal clear. Nothing to write home about. Peanuts. All right, cool.
So gradient is like the speed, how in total changes? Like,
It basically shows you what if I change my W5 by that value, then it will increase by 1 unit. Okay, that's what it shows. If I take the negative step, then it will show me and how much should I change the function so that the error decreases by 1. Okay, cool. Yeah. By the way, you have asked way too much by now. I don't know who else was talking. Who else was talking? Sorry. Who else was talking? You already got one. Go, and then we will have one.
Great. We are just taking like first derivative on W5 in this equation, and it's not that if we are doing it for all weights, it's not related to the total differential.
So basically we are taking, so this is a complex, the gradient contains parts, so the gradient would show you the direction along all the weights. So the gradient would be a vector of as many weights, as many, of partial derivatives. So we are now taking the partial derivative, and we'll have to, if we go really like this, like coefficient by coefficient, I have to take each one of them separate. But we're not going to do it, here I'm just visualizing how you do it for one weight, but the gradient is actually a bigger thing that contains the directions for all the weights at the same time. So you would know at the same time you update all the weights in one go. Okay? Cool. Any other questions? Yeah?
Is bias of a concern in updating weight?
Yes, bias is also part of that whole picture. Yeah. I almost hit this lady. Sorry. Anyone else wants to try their destiny? German, do you want to give it a try? Give it a shot? I'm already trained enough. Okay. Give me a bleep if you want. Anyway, so now the top part comes in. Chain rule. The derivatives. The chain rule. What's the problem here? What's the problem? The problem is,
For this example, you're doing it independently regardless of other.
sorry?
For this example, you're doing it independently regardless of other ways.
Yeah, that's a setup. That's a problem by setup. I completely understand, meaning that it's a waste. Just doing this is wasteful, because I would normally do it for the entire thing, matrix-wise. I'll show you how to do it. This is wasteful. This is part of the problem. The other part of the problem is that total error is a complex function, which is somewhere there uses W5, but it's very kind of much like this, one on top of the other on top of the other. So we'll have to break it down. The total error, we'll have to break it down into multiple functions. And if you know how to take the derivative of a complex function, is basically one way to go is called chain rule. Chain rule is basically the idea that you take derivatives with respect to those functions that are comprising a bigger function first, and then you go inside those functions, and inside those functions, and inside those functions. That's what chain rule is about. And we're going to look into this. First of all, let's remind ourselves, how did we arrive at E total, the error total? How did we arrive at this number? What was the formula that we used to arrive at E total? Sum? Of what? Exactly. So we have, in order to get E total, we have summarized the E of O1 of the output neuron 1 plus the output neuron 2, the error on one neuron and the other neuron. Now, so that resulted in this. So we basically, the first stop in our chain rule is to understand how the E total depends on EO1. So how much this influences this. The end goal is to understand how W5 influences E total. But in order to understand that, we need to break the complex function, which is E total, into smaller chunks. And this is what exactly we do here. All right. We go in here because why do we go into, so the next bit will concern only EO1 and not EO2. Why?
Because
Because
the word was used to calculate the EO1.
Because W5 has no influence whatsoever on the other one, on the EO2. Has no influence, whatnot. There is no influence. See,
If it would be only one, for example, W1,
it would be going both ways. Yes, you're right. So here I'm going to the EO1. So tell me, what's my next stop in the chain rule? What's my next stop of the chain rule? So you can actually get the pattern. So this one go up, and there will be something on the denominator place. So what am I going to? I'm going to look at how EO1 is influenced by
in between.
by
It was like in between something.
in between something. But what is this something? No. That's too soon. Too soon.
the prediction.
The prediction. So how this influences this, right? So the output of one, how does output of one influences the error on the first output neuron? So that's what chain rule is all about, is to go through these kind of steps. Now, what is going to be my next step? What is going to be my next step? You don't know? Okay, that's fine. Sorry? Wait, what is going to be the next step?
W5.
Not yet, too soon. So wait, what is this value depends on? What this value depends on?
And vice.
Not yet. So if you look at the, so if I go back a little bit just to show you the structure of my network. Gosh, I hope that I will be able to show you the structure of my network. Nah, whatever. You can kind of see it's true, but yeah. Anyway, so there is a neuron here. So what this value depends on? Some of the inputs on this neuron here.
Plus size.
It actually depends on the input, exactly as you were saying. So basically, there's a neuron here, and this value depends on the input of that neuron, right? So whatever comes in here produces this. But we need to understand how much changing this will change this in order for the whole chain to work. And now finally, what's my last stop? With respect to W5, how does this input depends on the W5? So that's the chain rule. That's what essentially every backpropagation algorithm, basically an algorithm that tells us what are the good ways for my neural network to solve the problem. This is eventually how it looks like. It's understanding the chain rule. There are easy pieces of this, and we'll have to solve this equation now. So there are easy pieces of this equation, and there are more complex pieces of this equation. So let's take it. Yeah.
The out divided by in1? No, the one before.
Come again.
The division that is before the last one.
This one.
That one represents the function you're using on the mean.
Yeah, it's no. This one is just a sigmoid. So input already contains b.
Okay.
So input is a W5 times the whatever was the output of the first hidden layer. Then it times this other W times the output of the second neuron on the hidden layer plus b. Okay, so this is already in here, inside here. Then the b will figure right here. This will be there. Any other questions? I know it's a little bit, could be a little bit over the hat, but asking questions helps to understand.
What if there is loop, like if we would have one more layer, then
What if we would calculate, let's say, the dependence of W1, which influences both of them, right? We would actually then go and understand how W1 influences both neurons, and then we'll summarize this influence. That would be the way. There wouldn't be a loop. It would be just that we would calculate it in both ways. All right. Now we're going to solve that using the chain rule. Right? So this is actually a chain rule. Basically, this is the chain rule. So the way to solve this, one other way to solve this d total dw5 is to write out the formula for e total, then write out the formulas for each of the errors on each of the neurons, then write out the formulas for the output, then write out the formulas for the input, then take the derivative out of that. And the chain rule is just something that helps us to make it, kind of put it into chunks, okay? Now, chain rule. The E total is the sum of two errors on the first neuron, output neuron, and the second output neuron. I want to take a derivative of this magnificently complex equation with respect to EO1. What is the result of that? What is the result of that derivative? So I'm taking that formula here, and I would like to understand this absolutely heartbreakingly complex issue. How am I doing this? Look, what if I say that this one is x and this one is y, and then I turn this into x and y? Derivative of x, it's 1. It's just 1. Does everybody see that? Just basically, I can break it down even more and have x dx and have y dx. So I hope everybody sees that this is 0. There's no x to take derivative of. There is just one x here, and the derivative is 1. Right? So this is so that means the derivative with respect to EO1 is 1, and I would like to understand what does this actually say. What does it say? For the what does it mean for us? So we were calculating, we were trying to understand how E total depends on EO1.
it's proportional.
Sorry?
It's proportional.
It's proportional, it's linear. The EO1 grows by 1, the E total grows by 1. Easy peasy lemon squeezy. You increase one by 1, the other one increases by 1. Because they just sum. This is a sum. You don't have any coefficients, whatnot. There's no square or whatever things happen. So if you increase EO1 by 1, then the other thing increases by 1. Questions? And we're going to do that for the rest of the equation. At this point, people like stand up and like, no, thank you. No. Bye-bye, see you. So we know one of the values, right? We have just calculated this, and that is equal to 1. Nice. The next candidate in line is a lot more complex. The formula is like this, and we're taking derivative with respect to out of 1. So like this. Who can show off some amazing derivative skills. So we are taking the, let me see, I'm a little bit simplifying this here. So again, x minus y squared, then this 1 over 2, x minus y squared over 2, and the derivative with respect to y. So now it's with respect to y.
-1.
No, it's
One.
it's just y.
So this is a complex function. How do we solve complex functions? We multiply, so we pretend like we take derivative of x minus y here. What if I take the derivative of this with respect to x minus y? What would be the derivative value?
Y minus x.
X minus y.
So 2 will go here, this will cancel out, and then I will have x minus y. Right?
X minus
No, x minus y.
Wait. Yeah, I see a lot of kind of thing happening. Basically, I can, again, so sorry. So again, I took this part. This was the part that I told you that let's take the derivative with respect to x minus y. And what we are left with is this, and we take the derivative with respect to y, and that's going to be -1. I hope that everybody sees that. And then I multiply with what I have left, and when I multiply with what I have left, it would be y minus x. Heartbreaking? Is it completely extraterrestrial? Okay, so this is going to be, so if I return back to my original values that I have been looking at, it's going to be out of 1 minus truth. This is going to be how much my EO1 depends on out of 1. Okay? And it's going to be 0.75. So I plug this back into our equation, and we go on. And we arrive at the peak of the excitement in this lecture is actually taking the derivative of the sigmoidal function. So here's the derivative of the sigmoidal. So this is a sigmoidal function, and we have to take the derivative with respect to input of 1. Thankfully, there is a shortcut, and the shortcut looks like this. So the derivative of that whole horrible thing equals to this. There is a shortcut. You can check it yourself. You can actually take the derivative yourself, and you will arrive at this point. I'd done it some years ago when I really wanted to go rogue, and it does look like this. So this is a shortcut. So you take it on your own. You have to believe the person that is telling you that. By the way, don't believe anyone, especially me. I'm always lying to people because I always forget stuff, and then I say things and they turn out different. Anyway, so it's going to be 0.75 times 1 minus 0.75. And the value is going to be 0.186. We plug it back and we summarize. So we are almost done. We are almost done. Now, the last thing, we would like to take the derivative of the input with respect to W5. If I write out the input formula, it's going to be like this, if you remember, right? This is how we calculated the input of the first output neuron. And now I want to take the derivative with respect to W5. Your time to shine.
The rest of them is over. It's just out.
So if I want to take the derivative with respect to W5, do I have it here? Okay, so you have it here. Now I actually will break it down here. What is the result here? What is the result here? What is the result here? Do we have W5 here? No, we don't have W5. So whatever you have, if you don't have the thing by which you take the derivative, you just say it's 0. The result? 0. The result?
Outage.
Sorry?
Outage.
Outage 1, yes. And that's it. That's all there is to it. Easy peasy lemon squeezy. And then you have 4 chunks of that horrible chain rule. You multiply them together and you get a value. Now the question here is, what the hell do values says? What the hell is this? What the hell is this value?
It's the contribution of this double five to
It's
error.
so let me ask this question another way. If I increase my W5, what happens to my total error? It also increases because the gradient is positive. So if I increase my W5 by that, in theory, the total error should also increase, right? And that's what it says, basically. So what we have to do is not to increase the W5, but to decrease W5 by that value. So that's what we're going to do. So basically, in order to decrease the total error, we take the gradient, the partial derivative, with respect to this weight that we wanted to check. And then we take this value of that weight. In our case, I think it was something like 0.4, or no. And then we decrease by the value of this partial derivative that we have identified. There is one catch though. And the catch is, if we make a big of a step, then we might overjump the minimum. So sometimes these cost functions are like this. And with that step, you might be actually going too far. You might be getting yourself into trouble. So instead of making this full step like here, we actually usually we take a smaller step. And the smaller step is this step multiplied by a coefficient that it decreases it. And we usually use something called learning rate. So this is the learning rate. If you heard about learning rate, this is exactly this. It's a caution of how careful I am about updating my weights. How, let's say, I am conservative about my weights because I don't want to overshoot. And that's what learning rate is meant for. Now, so I'm going to update my weight. I'm going to use learning rate of 0.5. By the way, normally, what's the normally, does anyone know what normally the learning rate is?
0.001.
0.00001 blah, blah, blah. So very small. Why is that? Why the learning rate is so little?
Make sure we don't miss any level.
Because usually when you calculate the gradient for so many weights, you really want to be really careful. Because when you update your millions or billions of parameters, then you can really get yourself very far. And you want to be very careful. You want to make very small steps because this wobbly field of cost function can get you to some kind of weird places. So you want to be really careful. Here I don't have to be careful because I have very few weights. I don't have to worry about that stuff. But I'll just be moderately careful by just saying 0.5. Yeah, so this is what I do. I multiply it, I kind of change my W5. I recalculate so I put in new W5 in the network, and I recalculate my total error, right? This is the one I wanted to decrease. This is what I want to calculate. So my total error is going to decrease if I update my W5. Now the question, what about the rest of the weights? We have just done it for W5. Well, the rest of the weights also should be updated. So we should actually calculate the same thing for the rest of the weights. Then let's say we have updated all the weights, and now the total error is a lot smaller. If we repeat this operation many times, it's going to, well, somebody already said overfit to the one single data point, but essentially we will decrease the total error very significantly. And imagine that this was just one point, but when you fit in all the points and you decrease the total error for all the points, you will essentially have this very nonlinear decision boundary, which will be able to differentiate between two parts of the spiral. Now, having said all of that, obviously, no one does it the same way. No one actually calculates chain rules for every weight in your network. This is all done using matrices. And this is what we're going to do in Python as well. So we're going to do it with matrices. In order to visualize, to illustrate you how is it done using matrices, I have reconstructed a different neural network, a bit smaller neural network, because it's much tougher to understand how this backpropagation thing works on matrices. So basically, we have the same problem. We have input layer, and we have one output layer. Straight away, we have an output layer, which doesn't have activation functions. So these symbols mean that we just sum up the weights, and that's it. Sum up the input time weights. Okay. And then we have the predictions, and then we calculate the total error. So all the same kind of stuff, except that we don't have another layer and we don't have sigmoidal functions inside. Any questions about this setup? So I'm just making the previous network slightly smaller and more manageable so that we would understand what is happening. Okay? Everybody? It's fine? I know you aren't. You don't ask some questions. Questions? Let me give it a try. I'm too weak. Questions!
Difficult to say.
It's already difficult to say. Okay. So that's how the feed-forward would work in this case. We would multiply x vector with w. We add the weights, we get the predictions. What does this mean here? What does this mean?
We compare it to the truth.
We compare it to the truth. So t signifies truth. So we compare it to the truth and we get the total error. Okay? Now the backpropagation side. So basically what we want to know is how does w influence the total error, right? We have to use the chain rule again here. So we'll have to use the chain rule. So we basically try to understand how this value is influenced by these values, by all of these values. Not one, not two, but all of them. By the way, having said that, what is going to be the size of the gradients for this matrix? How many partial derivatives I'm going to have?
The same as W.
So the same shape as W. I'm essentially going to have 2 by 2 matrix. And I'm going to do matrix 2 by 2 minus another matrix 2 by 2 times the learning rate. Right? Previously it was one value, but now it's going to be matrix. Okay, cool. Now, what is my chain rule? What is my chain rule? So the first thing that feed total depends on is the predictions. Right? Now, if I look for this in terms of matrices, my predictions are calculated exactly the same way. So there's still truth minus prediction squared, and then there is this 1/2, and I still take the derivative with respect to predictions in P here. And this is going to be exactly the same derivative we just have calculated with you. But remember, we have this truth and auto 1, this kind of thing, squared, and these things. So if I calculate this derivative, it's going to be 1/2 times 2 times minus 1 times t minus p. And it's going to be basically p minus t. We have the same thing, we just done it. But we've done it on this kind of individual value basis. Now we do it on the matrix basis. Another thing, or next step, is how the predictions, because we don't have just the hidden layer, the middle layer, we only have the input layer and the predictions. So now how does W influence the P, influence the predictions? How does W influence P? How does W influence P? Right? No? I lost you at some point, so let's recover. Let's recover. The recover operation. What the hell is happening here? What the hell is happening here? Describe any. Sorry? I can't hear you, sorry. Could you speak up? I can't. What is happening here? Say any random words, I will be fine. Don't worry. Matrix, slide, color.
Anyone want to know how the prediction is influenced by the weights?
By the weights. Right. How do we calculate predictions? How do we calculate the predictions? Wait, I know you know. Wait a sec. I know you know. I know you know as well. Out. How do we calculate predictions?
Well, we just input the point coordinates, and then we fill in the formula with the weights we have trained, and then we should get predictions as percentages, P1 and P2.
They're not necessarily percentages, but so how do we get predictions from this formula? How do we get predictions? How do we get predictions?
We sum this.
We just calculate it like this, right? So we take the input, we multiply by W, and we add the biases, and this is what the predictions are. So this is it. So now, what if I want to know how my P is influenced by W? I have to take the derivative of that with respect to W, right? Because everyone sees that. So this is the formula. You don't have to look here. This is the formula how I get predictions using W. If I want to take partial derivative with respect to W of this formula, I have to basically take the derivative, right? What would be the derivative?
It should be in sigmoid.
No, we don't have sigmoid. Remember, I told you that this is a simplified version without sigmoid. Wait,
I have a question.
Go ahead.
Okay. So, because I know that the derivative will be regarding to the x and y, and that's it. But how we then can adjust the bias?
Biases will be adjusted separately. Biases are adjusted
It's not
separately.
going into this derivative.
Yeah. Biases are adjusted separately. We're going to calculate separate partial derivatives with respect to biases. We'll come to that.
So just to summarize, so in order how we influences the result as a prediction, you need to take the derivative regarding to.
With respect to this formula, yeah.
Yeah. So am I getting it right?
Yes, you are. So here we took the derivative with respect to basically we were just asking questions how the E total is influenced by predictions. That's why we took this derivative. That's why we have it here. And now, oh my God, why are you doing this to me? And now we're going to take the partial derivative with respect to this formula here. What is the partial derivative here? It equals to what? X. Actually, it's going to be equal to X transpose. But that's because of matrix stuff. So it's going to be X transpose, but you're right, it's X. X transpose. You can think about this as a regular formula, the one that we used to have before. It's just now these are matrices, and that's it. That's why it's transposed. So now, how am I getting E total with respect to W to dW? How do I get, what am I supposed to write here? We have done the chain rule. We have done one part of the chain rule. We have done the other part of the chain rule. Remember I told you that I'm going to suck every bit of a calorie out of you. Now I think you get it, right?
It's I minus E times X transpose.
Yeah, exactly. We're going to multiply this by this. And by the way, we couldn't multiply them the other way around because the matrix multiplication has this very interesting peculiarity that you can't multiply all the matrices you like. Some of them will multiply and some of them won't multiply, depending on the dimensions of these matrices. Things become even more complicated, but that's okay. Now the question is about biases, right? So how do we do the same thing with respect to biases? The thing is, we keep this part of the equation because we still need to understand how predictions influence the total error. But now what changes is the second part of the equation. Now we don't take the derivative with respect to W, we take the derivative with respect to B with biases, right? So what would be the derivative here? Partial derivative. 1. It's going to be 1. You definitely already deserve a second. Okay, team. Good catch. Good catch. Yes, it's going to be 1. So that is it. Basically, now we have the chain rule, and we also can calculate the update for the biases. Right. Now we can update the weights. So we have the old matrix of weights. Now we subtract the updates that we have just calculated. They're going to be 2 by 2. And we multiply it by learning rate. We do the same thing for biases. Exactly the same thing for biases. Yeah, go ahead.
Is there any game to use different learning rates for different
Now that you asked this question, I don't think I remember anyone literally doing layer-wise learning rates, really. Could be, but what usually people do is not this thing, but actually they increase the learning rate. So that in the beginning of training, you have a slightly bigger learning rate. So you make bigger steps. Because in the very beginning, you wake up in the darkness, and there's somewhere there's a light. And in the very beginning, you can make bigger steps without the fear of, overjumping the minimum. But once you get closer to the source of this light, you understand that there are multiple places you can go, and that's where you decrease the learning rate so that you wouldn't somehow jump over the pit that you need to go into. And that's why what usually people do is that they start with a bigger learning rate, and then as they learn, they decrease the learning rate. This is called learning rate scheduling. And there are hundreds of ways you can do that. You can also do cyclic learning rate. You can then increase the learning rate, and then again decrease the learning rate, and then increase the learning rate, so on and so forth. So yeah, there's a lot of the whole bunch of science behind it, how you do it. And that's a very interesting question. Thank you. Nice catch. It was like a pro, like no C catch. So cool. Right. I wanted to finish the theory part. So actually, I was planning that we will do some practical part, but before that, I wanted to show you, how many of you know Playground, the TensorFlow Playground? Okay, not many of you. And I want to show you that if the internet will be kind to us. By the way, some references. By the way, somebody already asked me if I can share the slides. I'm absolutely happy to share the slides. I will share the slides. So wait, first of all, I'll mirror the screens. Yeah. Mirror. Now I'll see the same thing as you guys. So that will be, oh, what the hell is happening? Oh, my internet. Guess what? No, it actually works. One sec. Right, so the thing is, here we are, spiral. Ladies and gentlemen, spiral. The idea is, we need to build a network ourselves so that it is able to tell orange from blue points. So it builds this kind of nice curvy decision boundary to separate the one class from the other. What is the key thing about making it solve the problem? What are the key things we need to do? So we can add neurons here, we can add hidden layers, we can change the learning rate, we can change the activation function, we can add regularization, if you know what I mean. We can add the regularization strength, and we also change the problem. We're not going to change the problem, but essentially we can add neurons to layers, we can add layers, we can change the learning rate, we can change the activation function. What's the key to making it solve the problem? What is the key architectural choice that I'm kind of trying to get out of it? The thing is, if I run it like this, it's not going to work very well. And the reason why well, it's kind of nonlinear, if you see what I mean here. It is kind of nonlinear, but it's still going to struggle. You see, it has a nonlinearity. So tongue is nonlinear. If I take linear, for example, then this will be a problem. This would be a big, big problem. But so the one key thing is that we need to have a nonlinear activation function. For example, real loop. The other key is that we need to have enough neurons. We need to have enough neurons to capture enough patterns in the data. And then we also need to have enough layers of neurons so that they would be able to build up this kind of abstract representations of those patterns. So let's give it a try with this kind of simple thing. You see that this is basically, by the way, so how do you read the input here? So this is x2. Basically, this is, you see a horizontal line. It's basically judging my points based on their y location, y coordinate. So the higher the point, the more it belongs to blue class according to the whatever is drawn inside, and more the point to the closer to the ground, the more it's orange. And this one is actually x-axis. So I can add inputs. I can maybe multiply one by another. I can take a square, and so on and so forth. So I can actually add more flexibility this way as well. But you see my ReLU enabled neural network suffers. It doesn't do well. So what we'll do is I'll leave you this as a homework exercise for today. So you can practice in your amazing palace room and really make it solve the problem.
Why does PDE sinus of X would change its addressing?
The thing is, now that so here, every time I'm hovering over a weight, by the way, you can see that why I love this visualization is that it's really intuitive. You have a bigger pipe, means a bigger weight. You have a smaller pipe, means a smaller weight, and so on. And now somehow everything here relies on these two things. It means that you can build only this limited number of patterns with these x1 and x2. And these are by the way, these are the patterns that it builds. So what does this mean, for example? It means that everything on this side of the line is going to be blue, and everything on that side of the line is 0, because orange is a negative class. It's going to be a negative class, but actually, I have an output neuron somewhere here with the sigmoidal activation function. That's why I'm able to color in orange and blue in this picture. But otherwise, if I wouldn't have it here, then I would have white and blue. I would only have two colors, white and blue. But now I have both of these colors because this neuron actually has a sigmoidal activation function. So it actually has an activation function of its own. Basically, your homework exercise is to tweak this architecture so it solves the spiral. Okay, cool. Now, I sent you a link into Slack with this notebook. I hope that you can see the link in Slack. That would be the first victory. If you can open the link, it's amazing. Like Icon, for example, was my very VIP internet.
I think that they updated something.
Sorry?
I think that they leave out.
I have a separate modem here. I have a separate sources. I have a separate channel. Yet I am not there yet. And you see that it takes a bit more time. Anyway, so if you are in the collaboratory, how many of you opened the collaboratory? Why is my very VIP source of internet is not VIP source? I wasn't given enough credentials, so let me try it again. I think we just have to wait. We'll figure it out. Look, it's there, it's getting there, it's getting there. How do I try the networks?
So, _1, yeah?
Okay.
NGS.
I think I tried that. Anyway. Yeah, okay, thanks. All right, see, I'm already on meeting. See if I get. Guys, for those of you who opened the collaboratory, check file, copy to drive. So you need to save your own copy. So you won't be able to modify my copy. You need to save into your own drive, your own copy, which you will be able to modify. Okay?
Refresh.
Oh, refreshing. Okay, cool. Yeah. Refreshing. Oh, this was fast. This was fast, but not fast enough. That's okay. We're getting there. Getting there. Getting there. It was working before we started, so.
I mean, the best way is actually it works on my computer.
Yeah.
Maybe I should switch off the modem. Yeah, I should take it off. Let's try it. Let's see what happens. All right, that's so nice. Maybe it's already given up on me. Maybe it remembered me somehow IP address and just decided not to go for it. Otherwise, I'll.
I think it might be Google Colab.
You mean the collab thing?
No, I call it.
I mean, you can do something like this. And see that. Oh, look, it actually is there. Right. Hooray. Thank you, God of the Internet. You came to us. Wait, and now the next thing is to run the first cell. Anyway, to have. Do you know how you guys can call corgis and kittens and everybody, right? You know corgis and kittens? No? How come you survive until now and you don't know the corgis? And crab modes and so on. You go to what? Settings, miscellaneous, corgi mode. And you save. And I'll have corgis right now. You see, just and that's it, I can leave now. So again, for those of you who didn't catch that, so miscellaneous, corgi mode, or kitten mode. By the way, I like kitty mode more than corgi. So now I will have kitties walking on my screen. But don't get yourself. Oh, kitties do not show up, but anyway, they will at some point. All right, so we will not have time to finish this practice session today, but we will finish it tomorrow, and we will start from the next thing tomorrow. So what I want to do, ladies and gentlemen, here is I want to replicate our success in Python code. I want to do the same thing we have done now in Python. For that, I will recreate the spiral, but now in my code, I'm going to run a couple of setup cells. So you can follow me and run the same setup cells. So here's this data that I'm going to generate. I'm going to generate 100 points per class in 2 dimensions, x1 and x2. There are 2 classes. There are 2 classes, reddish and purplish, like we had in the lecture slides. And this is the code that does that. Well, not yet generation, but at least initialization. So this code does generation, and now I can visualize it. Here we go, my spiral, ladies and gentlemen. So this is the spiral that I'm going to try to crack with the help of AI, the almighty AI that we're going to write up today. Before I start building almighty AI, omnipotent AI, I'm going to pre-process slightly my labels. So my labels right now, my y variable is like this, 0 and 1, the vector of zeros and ones. Now what I want to do to make it compatible with my architecture is I want to transform these labels into one-coded matrix. Does anyone know what one-hot coding is? What does one-hot coding means? What does one-hot coding mean?
Is it as A and the other variable as B?
Yeah. So if you have two classes, you will have two columns in the matrix, and every time the class is 0, then you will have 1 in the first column, and if the class is 1, then you will have 1 in the second column. Okay, this is one-hot coding on basics of one-hot coding. So this is how I'm going to do it. And if I visualize 5 first points, the ground truth, remember the truth variable, right? And I'm going to call it. For 5 first points, I'll see their classes. So now, can you tell me what is the color of my first 5 points? Looking at this output, can you tell me what's the color of my 5 first points? Yeah. So how do you know? It's not purple, it's red. Why is it red? Because look, we have 1 in the first column. This means class is 0. And if the class is 0, it's red point. If I look at the tail, so I've been looking at the head of my truth variable. If I look at the tail of my truth variable, what's the color of the points that I have at the tail? These are the purple, because the 1 is in the second column, right? You know how the Python counts, right? It counts from 0. So the first column is actually 0 column, and the second column is actually first. Well, not first column, but column 1. So in that sense. Yeah, my kittens, nice kittens. Now what I do is I randomly initialize my weights and my biases. And I'm going to run a very simple neural network like this. This is the one that we had at the end of the lecture. It has only inputs and 2 neurons with the summation, which basically just sum up the weights. That's it. Very simple architecture. Does everyone understand this architecture? Could you ask me some questions? Do you understand the architecture? Do you have any activation functions in this architecture?
No,
Some.
But
Some.
we don't have? Or we do? We must have.
Some.
We just have some. It's not an activation function. It's just summing up the input. So we don't have activation function here. So it's very, 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 very simple. Why do we have to keep it so simple? Because when we do backpropagation, we don't really want to pay much attention to the how the activation functions are propagated and things like that. So we're just going to be keeping it very, very simple. Nice. So, ladies and gentlemen, I have initialized my weight matrix, W, and I also have initialized my biases with zeros, because biases is something that could, they will figure out this, that's okay. Now, with this architecture, how am I going to get my predictions? What am I supposed to type here to generate predictions? So I need to type something in this cell to generate myself predictions. How am I doing this? What am I doing? Like, what the hell? It's written out there. Just open your eyes and look at it. Absolutely. Like, really, it's already actually there. Now, how many ways you know how to multiply matrices in Python? I know 3. So can you name some of these? How multiplying matrices in Python works? At. There's one way to at. What are the other 2? NP dot and? Just, but it has a kind of peculiarities. There is another one. So NP dot at and product. No. There's this kind of function called matmul. So matmul, matrix multiplier, and matmul and NP dot are almost the same things, except there are some minor differences at bigger scales. But we'll be using at. So I'm going to just write x at w plus b, and that is going to be my predictions. So that is it. This is all there is to a very fancy, almighty, scary AI. Well, that's a very simple AI, but it's already very scary and almighty. So that's how we generate the predictions. By the way, so this is just to show you that when I multiply matrices, how do I know what the shape of the matrix I'm getting out of this multiplication? And the way to do it is to understand that I cross out these close. So basically, this is the shape of one matrix. This is the shape of the other matrix, and the resulting shape is going to be the first index of the first matrix and the second one of the second matrix. So it's going to be 200 by 2. So and in which circumstance this matrix multiplication wouldn't work? So what should happen in order for matrix multiplication to be legit, to work? So the rumor says that sometimes when you multiply matrices, you get error message back, right? So what are the circumstances in which you are sent to hell by the Python language and not being given your matrix multiplication result back?
I think there is like the number of columns need to be matched to the number of rows.
These two values should match, exactly. You're right. These two values should match. So these two values should be the same. Otherwise it won't work. So if I would multiply 2 by 2 by 200 by 2, it will not work. Okay? Cool. Now I look at my predictions. And I'm asking a question. What am I predicting for our first 5 points? What am I predicting for first 5 points? Wait, you have a neighbor which has a very good scarf which looks like the ruler. Can you tell me what am I predicting for first 5 points? You have been very quiet. Let's. So look, these are the predictions for my first 5 points. What am I predicting? What classes am I predicting? What colors of the classes am I predicting?
Okay, could you show me the spiral again?
The spiral is here. The spiral is here.
Okay, yes.
Does that help? Okay, let me remind you.
Yeah, I can remember what the colors are. Okay. That's 0 red, that's...
So what am I predicting here? Ladies and gentlemen, help. What am I predicting here?
Red.
So, okay, let me be like this. What am I predicting here? Why? Why you say that? Because this value is bigger than this value, right? Whatever is with minus should be less than whatever is without minus. Very good. So we are predicting the class 0, and the class 0 is red class. The same we predict for all the rest of them. But how about this one? We don't know, right? So if I go to all I rounded up the values, so it doesn't show exactly what happens, but essentially it's just 0, 0, so it may not be determined. But it could be that the value is just so small it doesn't really show that. Does that make sense? Yeah.
So what's on the left and what's on the right?
So the first column stands for the red class. So if the score of the first column in the first column is bigger than the score of the second column, then we predict the red class. If it's the other way around, then we predict the purple class. Now, what may be a good question is, what is in rows, ladies and gentlemen? What is in rows? These are my spiral points. Why there are only 5 of them? Because I just printed out only 5. But I can actually print out how many there are points overall. 200. There are 200 points. 100 from one class, the other 100 is from the other class, right? Make sense, everybody? Questions? More questions? By the way, I correlate the satisfaction of my audience with the number of questions they ask. So more questions they ask, the more satisfied they are. So please make me happy by asking questions.
What is the prediction of the first row when you have zeros?
So I think there's very tiny value that it doesn't want to show. That's why we just can't see it, but it's probably very, very tiny. Or if it's really 0, 0, then I don't know, the thing will break and everybody is gonna die and it's gonna burn in flames. I don't know what happens. 0, 0. Probably we'll choose randomly, or we'll choose the first one. That's it. Any other questions? Thank you for asking question, and you will get a stretch. Yes. Sorry. It wasn't me. It wasn't me. All right. So cool. How do I now calculate the total error? Ladies and gentlemen, now we have predictions, 200 of them in fact. How do I calculate the error? 2 minus predictions, let's start with that. True. Predictions in the power of 2. Wait. Answer mafia. So do you know what answer mafia is? These are the people who know and they are following, and everybody else is like, what the hell is happening here? So it's important to keep your answer mafia happy, but at the same time, give other people also a chance to speak. So what am I tapping additionally here? What else is missing from that formula?
We need to dive by the number of dots.
Sorry?
We need to dive by number of, not dots,
Points.
Points.
Divide by.
No, not points, halves.
Multiply by.
No, dive by number of neurons. No.
Divide by the number of neurons.
Wait.
What are we missing here?
Divide the value.
By?
Divide the value by then possible.
We do it later. So this is this line here. That's okay. This needs to be done.
Yeah.
We need to sum up. Remember, we need to.
Sum up difference.
Zeros.
So what will this generate? What will this generate? This will generate a matrix of differences between truth and the prediction squared. But we want to have only one value, only one, right? So we need to sum up this thing. So we need to write NP sum and then square. Now I'm going to add something else, 1/2, which is not part of the MSc kind of formula, but it's just for this kind of, for the convenience sake. When we take the derivative, there is this square thingy that appears. So in order not to deal with that square, I'm just going to add a 1/2 here in front of it. So I'm going to just say 0.5 times this. Why am I doing this again? When we do the derivative, since we have a square, when we take derivative of something in squared, then we'll take that 2 out. And in order for them to cancel out, I'll just artificially, purely on my own behalf, adding 0.5. Okay? This is a purely convenience thing. Now I'll run it. And this is the total error value that I get, 0.507. By the way, if you have any problems in your collaboratory, and imagine you have normal internet, you can go to my collaboratory, the one that I do right now, and you can make another copy so that if you have made a mistake somewhere, you don't know where, and it just doesn't work, and you don't want to spend the rest of your life looking for that mistake, you can just copy my collaboratory and you will be basically on the same page with me, okay? Now, so 0.5 is the error that we are facing here. Now what we have to do is to, well, easy peasy, just do the backpropagation and change the weights. By the way, before we change the weights, we show this. Now, look at this picture, everybody. Everybody, look at this picture. Look at me and look at this picture. And tell me what is going on here. What is going on here?
We have switched classes.
Sorry?
We have switched classes.
We have switched classes. So basically what this picture shows is that the almighty AI that we have just built got it all wrong. It actually thinks that this side of the line belongs to the blue class, and this side of the line belongs to the red class. While we see that the actual points in the space do not seem to confirm this hypothesis, right? What else can you say about this picture?
It's okay at the beginning, or at the first point, and then just.
It's okay in the beginning, and it's not so much okay in the rest of it, right? What else can you say about the picture?
It's linear.
Sorry?
It's linear.
It's linear. And it's linear for a good reason, right? Because we actually don't have anything non-linear in our system. There's nowhere to find non-linearity in our system. My question is, why is it so stupid?
Because we got it.
Sorry?
Because we made it.
Made it. We didn't make it stupid. We were planning for a big almighty AI. And what you're saying? Why is it so stupid? Because it's random. This is the newborn AI. It will be very smart, but currently it's so stupid because it's a newborn. I was very stupid. Well, I actually wasn't so stupid, but yeah, there's some sort of intelligence that is missing right now, and it will learn. It will learn. We just need to give it a way to learn. So we need to actually teach it. That's how we come to backpropagation. We're teaching our baby AI to do better. Right, so a lot of matrices, a lot of stuff written here. The very first step is we need to understand how our E total depends on DP, right, the predictions. It's already written out there. Essentially, we take the, remember the formula for the E total, the error total. What are you saying? We will use runtime GPU, no worries. Maybe tomorrow, but anyways. So we just wrote the formula for the total error, right? It was 1/2 truth minus prediction squared. Now we need to take the derivative of that thing with respect to predictions. And that will be this. Again, this is about derivatives. It's not about so much about deep learning. It's just pure math. So taking derivative of a complex function, and that's how it will turn out. So I can just write it in short. What I need to write in short here?
Minus truth is predictions. Minus truth minus predictions. Alright, truth plus predictions. Predictions.
Predictions.
Yes.
That's the most important thing is to say yes, very confidently. Yes, I completely agree. I also completely agree. Predictions minus truth. Then here, by the way, notice that we are still dividing by number of examples because this thing doesn't go anywhere. So we are still dividing by number of examples. So if you just take the derivative again, then this thing will remain there. Now, how my predictions depend on my weights. Do you remember how did I get my predictions? It was super complex formula. Please tell me what was the formula. No. What is the formula?
X multiplied by weights plus bias.
Yes, x times weights plus bias. Right? So if I take the derivative with respect to weights, what am I getting? X.
Transpose.
Yes. Oh. Transpose, exactly. Thank you for remembering this. this. Oh, I'm sorry for not killing, almost not killing your neighbor. It's X transpose. By the way, X transpose, you just write it with .t. Okay? Julio. Now, what is that? What is that?
Bias.
Biases, exactly. What do we have to calculate to get the biases updates? So here we calculated dp times dw, but we now have to calculate dp times dv, right? How much my predictions depend on my biases? That sounds great. Always depend on biases. So how my predictions, and you told me the formula for the predictions, and you said, and I trust you, x times w plus b, dependent biases. What is the result of that derivative? With respect to b. Exactly, it's just 1. Well done. It's going to be, oh, sorry. Ah, gosh, before going there. Sorry. This should be there. This should be here. dp, db, not this one. So here I'm just trying to summarize what we've learned about W. Basically, there are 2 pieces of that formula. Remember, dp, dw times, what was the second thing? So if I want to get updates for my weights, there were 2 pieces of thing we have calculated. One is this x times w plus b. We took the derivative with respect to w. We got x transpose. This is part of it. This is here. Now, what's the second thing? We need to multiply it with. Wait. What we have to multiply this with? What else have we calculated? What else have we calculated? What else have we calculated? What else do we have calculated? Biases will be done separately. We're now talking only about updates for the weights. What else have we calculated? Error, what was it about error? Can you elaborate? Can you tell me the exact variable name that I have to write out there? Wait, the neighbor? Total error, elaborate? I mean, if I write total error here, it will not work. DE? I think it was total, right? Oh, there was TE. And then DP. So it was total error depending on the predictions. That is it. That is it, ladies and gentlemen. That is it. Wait, I just kicked out something. Oh, I didn't run this thing, so I doesn't know what the hell is happening. I just saw an error and I'm panicking. Sorry. Go ahead.
Why did you write the derivative total error was the number of difference?
Because that's what this remains when we have the. I think it was done for the stabilization purposes, actually. Now I'm thinking back to this, but also because this, in my examples in the lecture, we were dealing with 1 point, but here we actually deal with all the 200 points all the way. So straight away, basically, we're dealing with all the 200. We are essentially using, you know, that basically batch equals size 1 type of thing. So we are taking average of all the points, all the point errors, basically. That's what we do here. So that's why we divide it, is that we want to understand what's the average influence of every point error on the system. Trust me on that. Right, and we get to dB. How do I calculate dB? So we just calculated an update for W, and update for W was this, right? Now, how am I calculating the same thing for B now, for updates for the biases? So one thing remains the same is D total error DP, but what is here? What is here? No, go ahead, just say it. Summer school, nobody gonna, be very. dp, db. Yeah, that's right. But this is 1, right? Ladies and gentlemen, this is 1. So basically, there's essentially no need to do it. There is one problem though. What is the size of my bias vector? 2. Now the question, $100 question. What is the size of this thing? So it's 200 by 2. Now, do you see my problem? I want to update my biases, which are only 2 values. And on the other hand, I have dp, which is 200 by 2. What am I doing here? What am I going to do now?
I'm just copying the number from Can I just write the biases twice over each other?
But there are 200 of these here. So this thing is 200 by 2. This thing needs to be 2 by, sorry, this needs to be 1 by 2.
So we need to write the piece, like it's 1 and 1.
Just transpose it.
Well, come again, I didn't hear you.
Like, we didn't write here like, DB.
This is okay, so we just...
Should be like the one, but it's like
Wait. What are the other ideas? So 200 by 2, I need to make 1 by 2. What can I do? Who said that? Sum up the rows, right? So if I would sum up all 200 rows, I'll just get 1 by 2. That's it, right? So this is what I'm going to do actually. I'm just going to write sum. There's one problem though. If I just write sum like this, I'm going to sum up everything into one value. So this is not what I want.
we should say that.
We should say sum by column or sum by.
I need to say axis equal to. So I want to have just one row. Now currently it's 200 by 2. What kind of axis should I keep so that it sums up what I want?
First either 0 or 1.
0. And actually I also need to say keep dims equals true. Yeah, that's a little bit more complicated. But essentially these are the matrix updates that we have. So we have an update for W, so this is update for W, and this is update for biases. Do you remember what was the original value of our biases? 0, it was 0. Now it's going to be, what is going to be the value of biases now? What? Depends on the learning rate, right? What if the learning rate is 1? What is going to be a new value of biases? What are we doing with these things? What are we going to do with these things? These are our updates, right? So how do we update weights and biases? We subtract. So we subtract this. So what would be the new value of biases? 0.5, 0.5. Yeah. And we're going to do it right now. So this is the slide that where I showed how to update the weights and biases. Does anyone know the framework called weights and biases? We and WB thing. Okay, you should. This is a very nice framework called weights and biases. But every time I'm saying weights and biases, I remember the framework. Tell me, what should I type here? So I'm trying to update my W. Wait. I'm trying to update my W. It's very simple. I want to update my W. I know the updates. I know the W. What am I doing? W minus. W minus. What else I should type? What am I typing after W minus? Wait. What are you pointing at? What am I typing? What are you typing anyway? What am I typing? Learning rates. Learning rates. Then starting so well. What? What am I typing now? What am I typing? What the hell is happening here? DW, yes. Sorry, wait. DW. Why am I not using @ sign? Because that's not matrix, it's a scalar, right? I'm multiplying scalar by matrix. There is no need. Good. Whew. What am I typing here? Whoever. B minus
Learning.
ooh. And so wait, a surprise here. What's the surprise here? What am I typing here? What am I typing here? DB. Of course I meant that. Of course I meant that's right. Who? That was the first year of our AI, baby AI. And now let's look at the way how the baby AI has grown. It has grown, ladies and gentlemen, and let's see how much it has grown. It's grown quite significantly. So if I now, please, God of internet. Oh, go away, kitten. Thank you. Yes. Much better. So most of the blue points are on the blue, the red is on the red, but it's still linear, right? It's still quite linear. So by the way, one thing that I can do, you don't have to do it, just look at me, just look at what I do, is that I go all the way up, and the place where I have calculated predictions, and I'm going to recalculate my predictions. So I'm recalculating my predictions, and now I'm going to recalculate my error. What do you think is going to be my error? So it used to be 0.5. You have seen a new picture. What do you think would be the error? What do you think would be the error? What? Less? How much less? Give me a number. Give me a number.
0.0.
How much?
0.2, that's it.
0.2. More or less? Less. Less. Of course, less. How much? 0.01. It's going to be actually half of that, of this value. It's going to be 0.12. 2.1. So you were very close. You were almost there. Now, so what happens is that we take this wisdom, the knowledge, and we write it in the for loop. So here, automatic saving failed, doesn't matter. So I will just write up. Okay, but you can help me with that. Predictions. So these are the things I'm just putting together what I have just written out there and adding the for loop on top of it. So what are the predictions? How do I calculate predictions? X times W plus B. Thank you. Now total error. How do I calculate total error? Truth minus predictions. Power. Wait. Power 2 and P sum and 0.5, yeah, the convenience term, yes. Now, how do I calculate the partial derivative of total error with respect to predictions? Oh, that was a very simple.
Predictions minus truth.
Exactly, predictions minus truth, thank you very much. How do I calculate the partial derivative of predictions with respect to weights? Anna? No, don't touch me. I told you, right? The brain is going to be It's hurting. It should be. That was the point. X transpose, right? X transpose. Here, dp db 1. Updates for W. Oh, that's going to be fun. Okay. So it's dp dw times dp. Okay, cool. And here it was this horrific NP sum with a lot of stuff in there, right? It was dte, dp, it was axis 0, and then it was, I think, keep teams true. All of that to keep the shape that I want. Have 1 over 2. W here. What am I typing?
W minus learning grades times
dw. And whose brain is hurting most? Can you help me here? Times db. Yeah? Now I got this. Now I will run it, and I'll run it for 190 iterations. 190 iterations, and this is how my error changes. So it was going down, but at some point it got stuck a little bit. Why it got stuck? The error. Why did it got stuck? Sorry? It's local minimum. Why did we have this local minimum? Why was it so early discovered? So look, at the 20th iterations, I already didn't improve. Why didn't I improve after 20 iterations? Because it's a line, ladies and gentlemen, line. You can't really do much with the line. You will be rotating it until forever, but it will not give you anything more than what it has given. What do you think it's the accuracy of this approach? How many points we have classified into right buckets with the line that we were rotating for a very long time?
75%.
77 or 76%. 78. Ooh, we're lucky today. So here's the best classifier you get with the line. Not good enough, right? Not good enough. We have 4 minutes. 4 minutes to get better. I actually, the second part of the practice session that we won't have time for, maybe tomorrow, maybe we can start tomorrow, I don't know, maybe, is to increase basically make a bigger net. Our almighty AI turned out to be not so almighty at the end of the day. So we'll make it bigger and we'll train it again. But this AI has advantage, besides that it's bigger. What other advantage did you see in this AI? It has a ReLU, it has nonlinearity in it. And that is going to be important. It's going to be very important. Let's see, you know what? So the thing is, what we will do is I'll leave it to you. But what we'll do is I'll show you that there is a lot of suffering happening here. One of the main sufferings is how do you really backpropagate through ReLU. This is important and it's hard. I explain it a little bit here and there. But what I want to get to is I want to replicate the same neural network, but now using a framework called Keras. How many of you know Keras? Okay, so some of you know, some of you have heard about it. So Keras is basically a wrapper. It's basically a high-level description language that just lets you say, I want that layer, I want this layer, and I want that layer, and then it does everything else for you. Backpropagation, feed-forward, everything. You don't have to worry about none of that. So I'm going to set up the same network as I have just shown you. I'll basically have a dense layer of size 100 neurons, which will take in the input of 2 neurons, which is coordinate 1 and coordinate 2. Then I'll have the last layer, the output layer, which will have only k K output is 2 neurons. Remember we had in the lecture. So I'm going to basically initialize this network. I'm initializing this network, compiling it with a slightly different metric, slightly different error function, not MSE anymore, but something called categorical cross-entropy. So I'm kind of pretending like I'm solving multi-class classification problem for those of you for whom it makes sense. Now I'm going to run it. I'm going to run it for the same 150 epochs. Epoch is the iteration, basically. How much? I'm going to cover epochs tomorrow, so you don't have to worry about the epochs right now. And finally, my collab is happy because that was the first time I used GPU. So I'm using GPU right now. I'm going to calculate the score. What do you think would be my score? What do you think would be my score? 2-layer network with ReLU. 99, yes, it will be 99. And let me visualize it. So just with a little additional tweak, you can get from line to something reasonable. And yeah, that is pretty much it. So this is how my error was changing, was dropping. Yeah, as you can see, we call the error in deep learning, we usually call it loss. So error was just to kind of make it more familiar, but we actually say loss most of the time. Yeah, that's the classifier we have built, and I think I'll be wrapping up for today. If you have any last questions, that would be the right time.
Can we have the solution of the?
Yeah, basically, there's the other one.
Because of this sheet, because I didn't.
You can copy this sheet that I have right now. So that will have the solutions for the part that we have filled in. But the other part will not have solutions. I can fill it in tonight, and you can copy it if you like, or you can do it yourself, see for yourself. Sure. Any other questions? Still discussing. Okay. Let's wrap it up then, and take the questions to the informal part. Okay, thank you.